think lambda is not zero. Again,
So you're right, with the lambda. That's right. It's a Ricky zero, I'm saying. So yeah, that's what I will say. It's a kinematic. but with the lambda, the kind of solutions you get, essentially that is also not a fully a dynamic solution. But you have a non-trivial thing, but the potential coming from the mass point is constant. So that's the thing what we have. Now, whether can you make this dynamic? And obviously, you say it looks a very strange sort of thing. And to that, let me get back to derivation of the Einstein equation in a purely geometric manner. And from there, I would like to get a clue what to do. And that is to say that the universality of the gravity demands that it can only be described by the curvature of space-time. And now, if that being the case, then it's the curvature which should entirely determine its dynamics. You have no freedom to postulate a gravitational law, and that comes from that you have a Riemann curvature with you, which satisfies the Bianchi identity. We did nothing to this, means the Bianchi derivative is zero. And now you say you take a trace of this.
But why are the above features attractive to you? That in 2n plus 1 it's dynamic, plus 1 is dynamic. Why are you?
Oh, I do this simply because I have a one theory which is a good theory. That is what I want to generalize, which has this feature. Okay. If that's not good enough, let me give you another physical motivation. And that is to say, and the two will coincide there, that in any classical gravity theory if you have, you would like that the field of a mass point should admit bound orbits around it. Now this is a reasonable physical demand. And if you look at this, for Einstein gravity, this demand is only met only in 4 dimensions. Einstein gravity and Newtonian gravity are no different so far as this question is concerned. And simply because as the dimensions increase, gravitational potential becomes sharper and sharper. It goes as 1 over r raised to d minus 3, whereas centrifugal potential remains 1 over r square, irrespective of the dimension. So as the dimension increase, the centrifugal potential cannot match the gravitational potential, and no bound orbits. So if you ask the question this, that the bound orbit should exist, then this uniquely, it takes me a step ahead of to say, it takes me that to what you will call a pure law of gravity. By pure law we mean that it is not the sum over n, but it's only one fixed n. That is, for a fixed n, you don't sum over the lower orders. And that will have the property, the bound orbits will always exist. And you will immediately ask, how does it happen? Because what happens in higher dimensions? So the point is in the Newtonian theory or the gravitational, your Einstein theory, the potential goes as 1 over r raised to d minus 3. Here, the potential goes as 1 over r raised to d minus 2n minus 1 over n, where n is the Lovelock order.
What is small d?
Oh, sorry, small d is a capital D. So now, and this image will tell you, if d equal to 2n plus 1, the critical odd dimension is constant, like your BTG. And the next order, d equal to 2n plus 2, the critical even dimension, it goes as nth root of r. So 1 over n is always less than 2, and hence it is never going to overpower the centrifugal potential. And let's say the black. Now here, this demand uniquely picks up pure Lovelock from all the Lovelock. So no general Lovelock. It's only the pure Lovelock which will have this. We will come to the same conclusion from this end. So you have this, and this gives you your Einstein tensor with the divergence free, and moment I have the Einstein tensor, I can write the equation of motion for gravity. So basic question what we really want is, you want a second rank symmetric tensor. Now you ask the question, can I do this kind of a thing where I can implement this, that it is kinematic and all this? So first question which one ask is that let us try to define, generalize the Riemann tensor. So we ask for a generalization of the Riemann tensor, which is a polynomial, homogeneous polynomial in Riemann, but you could have an infinite number of homogeneous polynomial. How do I pick out one? So my ultimate question is what? I want an analog of this. So I really want is a nth order analog of the Einstein tensor with vanishing divergence. So we do the same thing, let us say. So you take a Bianchi derivative, you have Bianchi derivative. Here the Bianchi derivative vanished. Here the Bianchi derivative will not vanish. Because the vanishing of the Bianchi derivative gives you the unique Riemann tensor. You know. But then question is, my main question is, I want a second rank symmetric tensor with vanishing divergence. And for that, I don't need the Bianchi derivative to vanish. It's good enough if its trace vanishes. So you demand its trace to be zero. And that indeed gives me an analog of Einstein tensor with vanishing divergence. But now you say, but what it has to do with the Lovelock, how I am sure that this is. Now what then happens is that the tensor which I get by variation of the nth order Lovelock, the tensor which it gives me, say some HABN, and the thing is this HABN is equal to the tensor I get from here, the GAB. So that justifies that this is. So once I have a Lovelock Riemann, so let us call that a Lovelock Riemann tensor then I can ask this question there. So since I have a Lovelock Riemann, then I can ask in all d equal to 2n plus 1, in all odd dimensions, the question which we I'll ask is, Lovelock Riemann should be entirely given in terms of Lovelock Riemann. Now, this is what we have demonstrated in general by Kamano and myself last year. As a matter of fact, this result we obtained earlier, but that was a restricted, that it was more like constructing an example. We first came to this, showing this to be true for the spherical symmetric. You take a general static spherical symmetric metric, ask for the solution, and with it we could show that whenever the Ricci vanishes, the Riemann vanishes. Or that is, so what, so, but then we have now shown this in general, that in all critical odd dimension, the Riemann tensor is given in terms of Ricci. So whenever Ricci vanishes, the Riemann is there. And then of course as it is, so that is to say, in all critical odd dimension, Lovelock gravity is kinematic, and it becomes dynamic in the next even dimension.
You have to construct for a given and a particular Riemann, which has this property.
That's right.
So let me ask you the following. We know that if we put in matter, whether it is Lovelock gravity or any other dimension, in any dimension, if you also have a matter action,
Yes.
then if the matter action is invariant under diffeomorphism, then the corresponding energy momentum tensor is divergence free.
Right.
So from that, can't you automatically construct what should be the GAB? Because the Lovelock action with matter will give you a generalized Einstein equation.
No, so wait a minute. Let's come to this. So the matter action is going to give me this. Right. Right. But how do I get the left hand side? What it is
The
doing?
left hand side will come from the total variation of the metric for the
So-
entire theory.
No,
You will get
no,
a generalized Einstein equation.
No, right. What I'm saying is that what do I take? I take the Lovelock action for that.
Yes, for the gravity sector, take the Lovelock action.
No,
Take the matter action, then you'll get an Einstein equation. Something is equal to TAB.
Right.
If the TAB is divergence-less,
Yes.
the left-hand side must be divergence-less.
Of course, yes.
So that will automatically give you.
No,
uniquely-
that will give me, but that, how does that give me that it's in odd dimension it will be kinematic?
That you don't know.
Oh, so that is the thing. So there is no statement being made about that. That I said that you have the Lovelock is the general, the most natural generalization of Einstein, keeping the second order equation property. You have this, but now among the Lovelock, I want to come down to the pure Lovelock. The entire Lovelock is no good. And that pure Lovelock is identified by this kinematic property. That this property chooses that it has to be only the pure Lovelock with the one single term, no sum overs. So that's the thing you have. And then you say that this is in general. So the first statement that comes about is, so now from there what the picture comes about is this, or a sort of a general theme which emerges is that you have a gravitational behavior in these two, is correct. odd and even dimensions characterized.
One question. These conditions you got by imposing the conditions that classically will happen.
Yes, classical.
So in your calculations
Yeah.
or in your
Yeah.
transaction,
Yeah.
that is one of the inputs.
Yes, sir. Yes, that's right.
So
No, that's right. I'm only seeking a classical equation as a generalization of Einstein. It's a classical. That's right. And what happens is that these two things, so this demand and the kinematic demand, both have them single out the pure level. So both these are the motivation. More generally, so one of the things which of last couple of years we are involved in this is that the gravitational behavior or gravitational dynamics in these odd and even dimensions has a universal character. Well, odd dimensions, it is trivial to, so far as the vacuum is concerned, that it is a Lovelock. I must say here that here the vacuum is Lovelock flat by saying the Lovelock Riemann tensor is 0. But it is not Riemann here. Riemann is. But what about the Riemann? Riemann is due to what you have a curvature due to a solid angle deficit. In other term to say, if you try to find out in terms of the spherical symmetric Newtonian potential being constant. Now the Newtonian potential being constant, first thing you will immediately say, it should be trivial. But in Einstein theory, Newtonian potential appears at two places in the G0 and GRR. G0 it does the job of a Newtonian potential to give you grade phi. There, phi being constant is trivial because you could coordinate transformation you can do. But in GRR, it is non-trivial because if you want to redefine your R coordinate, the fellow props up in before the R square d omega square. So it produces a non-zero R theta phi theta component which going as a constant over R square, going as 1 over R square. And now this is the this space-time is approximates to the space-time of a global monopole asymptotically. If you look at the stress tensor for a global monopole, then it is T0 equal to TRR going as 1 over R square asymptotically. And that's exactly what it is, all others being 0. And so that's the equation. So it is a trivial at the Lovelock level, but non-trivial here.
So are you saying that for the regular Riemann, for this case, the geodesic deviation, there is no geodesic deviation. To geodesics, the second derivative doesn't vanish, but if you parallel transport a vector in a closed curve, then it doesn't come back to itself.
Yeah, right.
That's
yeah,
what.
yeah. It's so you will have a solid angle deficit. That's right. So you have an angle deficit so far as the curvature is concerned. Locally the curvature is 0 for angle deficit because you can transform it away. Globally it will be non-zero. But the solid angle deficit is locally also is non-trivial. So
So
that's
it is almost like a geometric phase type of structure because in a pairing phase also you have a solid angle deficit also.
yes. True. Good, it's something from, yes. Okay. So you're now, so this is the kind of thing which we have been looking at. So first thing you could ask is, okay, let's consider the static black holes. Now the potential for static black hole, that is the metric function which your G naught naught inverse of G R R is f of power, then it goes as 1 minus, let's keep the lambda for a minute and get to this lambda r raised to 2n plus m over d r raised to d minus 2n minus 1 raised to 1 over n. Now, interestingly, if I take its asymptotic limit r large, then it will go as 1 minus some lambda bar r square minus m over r raised to t minus 3. It goes to the Einstein de Sitter. Mind you, there is no Einstein term in the equation. We have only the nth order term in the equation, but it imbibes the Einstein character asymptotically. Of course, for that, the critical thing is the lambda has to be non-zero. Only then I can expand it for large R to include this. If lambda is 0, then you will have this or 1 over n and you can't do anything. Now, this is the thing what the BTG, your dimensionally continued black hole, they did. They actually have this lambda outside. So their solution is 1 minus lambda r square minus m over r raised to d minus 2m minus 1 over n. So it is a BTJ black hole with lambda, which can never agree to the Einstein solution asymptotically. But that's the yeah. So that's why you have all this. And second, of course, bound orbits already I talked about. That in this world the bound orbits exist, and they will exist only in the critical even dimension d equal to 2n plus 2. Not for any d greater than or equal to 2n plus 2. It's only in d equal to a critical dimension, or which is to say, given the degree n, the equation is a valid, good equation only in 2 dimensions, odd and even, corresponding to 2, 1 plus 1 or 2, 1 plus 2. So that is why, so Einstein equation is a good equation for 3 and 4 dimensions. If you go to 5 and 6, you should go to n equal to 2, and similarly. Second thing is, if you look at the thermodynamical parameters of this, like temperature and entropy, in terms of the horizon radius, they have a universal character in the dimensions, odd and even dimensions. So the relation, for example, in all even dimension, d equals to 2n plus 2, entropy will always go as the square of the horizon radius. Similarly, the temperature, the relation. So there is a universality in this. But this horizon,
So it's not area.
it's not area. Oh, area, if you want to look at the area thing, then this will be it will go in terms of area, another root of it. Yes. 5 minutes. Oh, good enough. That's right. So now let me tell you one couple of things to say, and then we call it a day.
So in a sense, differing from the conventional thing, the number of degrees of freedom supposed to reside on the horizon dramatically reduces.
Yeah. I'm going to say the last two, in this 5 minutes, 2-3 things to say. Among this, the degrees of freedom also. So, this is, now there is one interesting thing you have here, it's a this vector. So if you look at the, take the lambda 0, you have the potential going as this. This gives us to ask you one crazy question. Can I have this? So let's ask the question this. How about asking this? What she's going to tell us that you have d equal to what you have 3n plus 1.
Yes.
So d equal to 4, 7, 10, 13, so on, corresponding to n equal to 1, 2, 3. So I have the same Schwarzschild solution for n equal to 1 in 4 dimension, n equal to 2 in 7 dimension, n equal to 3 in 10 dimension, and with the same frequency. So you have the same solution here. Now this is something which you have just noticed last week. I don't know what can we make out of it physically, but it looks a very interesting coincidence. One of the things you could presumably ask is,
But you have dropped the lambda term now.
I dropped the lambda. With the lambda it won't come. No, so with the dropping. Could be that the Schwarzschild solution is stable, we know, in 4 dimensions. Now in 7 dimension, will it still be stable relative to the Gauss-Bonnet equation? Because there the equation is a Gauss-Bonnet, and similarly in a higher order. So looking at its stability will be one question, and by the remark that this kind of a solution, you can as well ask, how about its stability? And we are done. Now, in general, this is unstable.
Naresh, 4, 7, 10 are already known, I mean, this dimension. 13 is a...
No means
No.
Not with you.
nothing is known.
No, what I'm saying that, is it not the 4 plus 7 giving the 11 dimension?
नहीं है वो कहाँ सलाम yes salam walam की यहाँ जरूरत नहीं है this is something much deeper than salam don't do it so don't say yeah let's no yeah sorry it looks like this but I don't mean to do numerology it's not numerology whether there is some meaning to it we don't know so that's here for each stability in general unstable. But it requires lambda to be, in terms of lambda and m, you can give a range of r for stability. Because that lambda is required to be non-zero. And there is one more point I wanted to say, but I think that will be enough for that.
Questions?
Yes.
We started off talking about, what Einstein was doing. So he was trying to bring together Newtonian gravity and special relativity. Okay, so the question is, well, where is this potentially going? The key problem we've got is general relativity and quantum mechanics. Can this possibly help with that?
Okay, so the question, very good question. So as a matter of fact, we asked honest answer to your question is I really do not have such a compelling guiding principle to say that what I want to do. So, among the way the roundabout way I can say is that whenever you seek this kind of generalization, you really seek in enlarging your framework. So that in the Einstein, for example, when you said the whole thing he started by just bringing in the massless particle within the fold, first in mechanics, then with the gravity. Similarly, in the process, first he bound the space and time together, then he's expanded the framework by curving the space. Now here, in this case, only the one thing we are finding, the space-time is already there. What more can you do to it? And one of the things possible to do is that you can consider higher dimension. So it is on something, so if I am going to the higher dimension, then I am asking it, if you are probing higher dimension, then it's reasonable to ask the question, what should be the right gravitational equation there? And my claim is that this probably shows us the way that even in the higher dimension you want to consider that this should be the right equation. Yes.
In your kinematical case as well, where RAB is equal to 0 in the matter free case, that is the equation. But is it really trivial in the following sense, that if I start expressing my metric as eta mu nu plus h mu nu, I can still extract from RAB equal to 0 a wave equation for the HAB. So although RAB is equal to 0, we still have gravitational degrees of gravitational way of degree.
Good. This was another thing which I wanted to say, but I forgot. But now, since you asked this question, so this was the right question to say. That since D equal to 2n plus 1, vacuum is trivial. One would ask, say, in this, will there be any 3 degrees of freedom or not? Now this is the question recently with the Chilean friends we worked out, and actually they did. I simply coaxed them to look at, and they are generous enough to put my name in there because I won't know anything. They did a very detailed constant analysis, and turned out that you see the degrees of freedom remain the same as Einstein in this. And the degrees of freedom go as d into d minus 3 by 2. So we are considering the 5-dimensional case you have, so it remains 5, and you tell them. Now the reason for that is, one of the problems with this generalization is, for this Lovelock-Riemann, this fellow, I don't have neither the metric nor the connection whose commutator gives me this. I only have its definition in terms of the Riemann tensor. But what connection generates it I don't have, nor do I have a metric. And so when you are looking at that degrees of freedom, your field is the metric. And so far as the metric is concerned, that metric is not directly related to this. It's only implicit in here. And so the degrees of freedom, unfortunately, remain the same as in, that does not distinguish between Einstein and the Lovelock. But I believe that some point there will be a thing where we could do something better. Thank you.
I think that maybe, by the way, I think this probably follows, from the fact that in higher dimensions, the Helsinki group is replaced by some SO3 group and SO. So that is in the English.
Well, that is true.
Okay,
That is not related.
That's what I was.
That all came from there. That's no problem. But that is not related to my Riemann, you see what I
It
mean.
comes, it will always happen. So next, maybe I can talk to Professor Nigel Bishop will talk about this space and